So, one change to Dalton's atomic theory was that atoms are divisible into subatomic particles. We now know there are electrons, protons, and neutrons. Let's talk about each of those and how they were discovered. So first, the discovery of the electron was credited to this guy, J.J. Thomson. In 1897, he used an experiment called a cathode ray tube to deduce the presence of a negatively charged particle, which we now call the electron. Here's how his experiment worked. So he had this glass tube under vacuum, and he had a cathode and an anode in it. These were metal objects. He ran a high voltage electricity to the cathode. When the high voltage reached this cathode, it excited the electrons in this metal, and they were emanated from this cathode to the anode, or from the negative terminal to the positive terminal. And you could also see how the beam of what he called cathode rays were deflected or attracted to positive plates like on a magnet. The negative particle was attracted to the positive plate, but it was repelled by the negative plate. Here's how his experiment looked. So he's pushing it away. Now he's repelling it with the other side of the magnet, the negative side of the magnet. And you can actually control the cathode ray here, this magnetic field. So he also set up an experiment to measure the ratio of an electron's charge to its mass. And he found this charge to mass ratio to be constant. He didn't quite know what that meant at the time, but we'll see how it becomes important later. So because of this, Thomson said he thought he was ready to come up with an atomic model of what an atom actually looked like. So he believed that the electrons were like plums embedded in a positively charged pudding. So we call his model the plum pudding model. So here's what it looked like. So he imagined just this field of positive charges. These were the positive charges in the atom that were balancing out the negative charges that were just randomly distributed, kind of like fruit in the bottom of a yogurt. He called it plum pudding, though. So next, in 1909, a man by the name of Robert Millikan determined the charge and mass of an electron. He did that with this apparatus here, very famous experiment called the oil drop apparatus. Here's how it worked.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
So conclusions from his experiment was that the charge of the electron was indeed negative, and he calculated that to be 1.6 times 10 to the negative 19 coulombs. And using this charge and Thomson's charge to mass ratio, he calculated the mass of an electron to be 1/1840th the mass of a hydrogen atom, which is really light because hydrogen atoms are the lightest element on the table. They only have one proton and one electron. Next, the proton was discovered by Eugene Goldstein in 1886. He observed what is now called the proton, and it was determined to be a particle with positive charge, which balanced out the negative charge of the electrons. and the mass was 1,840th that of an electron. And his experiment was fairly similar to J.J. Thomson's cathode rays. He shot cathode rays and he noticed the positive charges, which were the protons, bouncing backwards. And James Chadwick in 1932 confirmed the existence of a neutron with a very complicated experiment I don't have time to explain in this video, but you can look it up if you're interested. And he determined that the particle had no charge and the mass was nearly equal to that of a proton. So let's review the properties of the subatomic particles so far. So electrons have a relative charge of -1. Protons have a relative charge of +1, and neutrons were neutral, so they have no charge. So think positive protons, neutral neutrons, and electrons are, of course, negative. The mass was determined for all these subatomic particles. That's the mass of the electron, and those are the masses of the protons. But due to the fact that those numbers are really small and kind of hard to work with, we deal with relative mass when we're talking about subatomic particles. So we compare them all to the mass of a proton. So electrons are so light compared to a proton, we say their relative mass is 0. Protons and neutrons weigh the same, so their relative masses were 1. So the location of these particles is also important. We'll talk more about this in the next couple of videos, but the electrons are located in what we now call the electron cloud. It's an area outside of the nucleus where the protons and the neutrons are located. So how we know the location of some of those particles is thanks to this man, Ernest Rutherford, and his famous gold foil experiment. It was actually a series of experiments that were carried out on his behest. He didn't actually do the experiments, but he was in charge of the lab that did them. He and his co-workers were attempting to learn more about the structure of the atom. Here's how they did it. So they shot alpha particles. Rutherford was pretty famous in the chemistry world for discovering alpha particles. He actually won a Nobel Prize on them. So he was very familiar, and he was using them in the lab to shoot alpha particles at a thin piece of gold foil. The particles that deflected off of the foil or shot right through the foil were detected on a screen, kind of like an X-ray screen. Alpha particles were radioactive, so when they touched the screen, they left a little dot. So here's how his experiment worked.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So his findings were that most of the particles passed right through. And if Thomson's model was correct, all of the particles would have passed right through, as you can see in this picture. Okay, but what happened was some of them were deflected. Few were greatly deflected, like directly back at the alpha particle emitter. He said it was like howitzer shells bouncing off of tissue paper. If you don't know what a howitzer shell is, it's kind of like a tank missile. And if you shot it at tissue paper, you would expect it to go right through because howitzer shells are really big and they move really fast. So is an alpha particle. Alpha particles travel 1/10 the speed of light. So if you shot it at this little piece of foil and it bounced off and came right back at you, it was pretty amazing finding for that time. So his conclusions were that the nucleus was small. It was surely small because most of his alpha particles went straight through and were detected directly in line of where the alpha particle emitter was shooting. It went right through the gold foil and directly to the other side. He also concluded that the nucleus was dense because when these alpha particles, which were traveling 1/10 the speed of light, hit the nuclei and bounced off, it said that the nuclei weren't moving. They must have been incredibly dense to withstand that kind of impact. He also determined that the nucleus was positively charged because the alpha particles he knew were positively charged. And if you follow these little green lines like this one here, if you see it traveling and it deflects slightly at this angle before it hits the other side, it's because it's being repelled by the positive charge in this nuclei. Also, the nucleus had to be positive because if the alpha particles were positive and they shot straight at the nucleus, they would have attracted. If the nucleus was negative, opposites attract. The negative charge would have been just attracted to the positive charge like a magnet, but it wasn't. So based on his findings, he decided to make an atomic model like J.J. Thomson did. This is kind of what he came up with. He has the nucleus in the middle, and you can see the positive charges, and the negative electrons are somewhere outside of the middle. So his model showed that the atom was mostly empty space, and that all the positive charge and almost all the mass is concentrated in a small dense center, which he called the nucleus. And the electrons were distributed around the nucleus and occupied most of the volume. His model kind of morphed into something that looks like this today, and it's kind of what we normally think of when we think of models of the atoms. But we're going to learn that this model, despite the importance of this very neat experiment, this model is still wrong. This isn't what atoms look like, and we're going to talk about how we know this not to be true and what we think atoms look like based on the current evidence today. So, atoms are made of subatomic particles, the protons and neutrons and the electrons. You should know the charge and mass and the location of each particle. These are very common questions on tests and Regents exams. You should also understand the gold foil experiment. It doesn't make the Regents exam every year, but it makes the Regents exam a lot. So you should understand how it was conducted and what were the major findings and why the conclusions were what they were based on the results of the experiments. And you should also know how this informed the model of the atom to what we know today, even though that Rutherford's model was slightly incorrect. And we'll talk more about the evolution of this nuclear model in the next video.